Good afternoon, and thank you for joining us today for this presentation titled Scott and Shasta Rivers, Fish 101. My name is Crystal Robinson, and I work for the California Department of Fish and Wildlife's Klamath Watershed program in Wairika, and I will be presenting today. We will begin with a discussion of the life cycle of salmonids as well as their habitat needs. I will then review the current fish distribution maps for the Scott and Shasta. Next, I will provide an overview of some best management practices you can do on your property to enhance fish habitat. Lastly, I will provide some information on the department's current funding programs available to assist landowners. The salmonid life cycle. Let's start with the eggs. Eggs are laid in freshwater streams and rivers. The female lays her eggs during the fall in a redd, which is a nest in the gravel, and the males fertilize the eggs. Embryos develop during the winter and hatch in the spring. Baby fish, right after they hatch, are called alvin. The yolk sac of the egg is still attached to their belly, and often this life stage is referred to as sac fry. This will be their food source for the next few months while they are still in the redd. After all of the yolk sac has been absorbed, the fish leave the redd and become fry. Fry will spend the next year or so of their life in the stream, eating and growing to size. The length of time spent in the stream depends on what species they are. Chinook reside in river for 5 months, coho spend 1 year in fresh water, and steelhead have a variety of life histories we will discuss later in more detail. After spending their time in fresh water, environmental cues trigger salmonid juveniles to head to the ocean. The fish then turn a silvery color. This is called smolting. Once they reach the estuary, smolt acclimate to their new salty home and feed heavily to enhance their chances of surviving in the ocean. Salmon can spend the next 1 to 7 years in the ocean, depending on the species. During that time, they migrate looking for food and grow. After a certain amount of time, salmon get the urge to return to where they hatched to spawn and start the cycle again. Once the fish returns to fresh water, they stop eating, so it is important that they move quickly. Once they reach their destination, the female builds her redd. She does this by turning on her side and flapping her tail against the river bottom, moving rocks and gravel. Once the redd pit is dug, males fight to spawn with the female. After a mate has been chosen, the eggs and milt from the male are released at the same time, and the fertilized eggs fall into the redd. The female covers the nest with gravel and guards it until she dies, around 2 weeks after the first mating. The first species we will discuss is Chinook salmon. As you can see in the photo, they have black gums at the base of the teeth and spots on both lobes of the tail fin, also known as the caudal fin. The Chinook salmon rears in the Pacific Ocean for most of its life and spawns in freshwater streams. We typically see Chinook salmon spending 3 to 4 years in the ocean before returning to spawn in the Scott and Shasta rivers. This can vary by year, and more specific information regarding this can be found in the department's annual salmon survey reports. Chinook salmon juveniles typically spend 4 to 5 months in freshwater before migrating to the ocean. These are critical times for optimal flow and water quality in the river. The majority of mature Chinook salmon enter the Klamath River from April through September. Different populations of Chinook salmon in a basin can be distinguished by the season of the year during which they re-enter the freshwater. Fish with different run timings tend to spawn in different parts of the basin and thus maintain some reproductive isolation. The Klamath River currently has 2 Chinook populations, spring and fall. Spawning generally occurs from September to early November for spring Chinook and from October to December for fall Chinook. All adults die within 2 weeks after spawning. Spring Chinook populations in the Scott and Shasta rivers have not been documented as present since the 1970s. Fall Chinook populations have been monitored since 1978 in both rivers. Next, we will review the coho salmon. This species is listed as threatened under the Federal and State Endangered Species Act. They are distinguishable by their white gums and spots that are only on the upper lobe of the tail fin. The coho salmon rears for part of its life in the Pacific Ocean and spawns in freshwater streams. Mature fish migrate into freshwater in the fall, typically spawning from November through February in the Scott and Shasta. All adults die within 2 weeks after spawning. Juveniles normally spend 1 summer and 1 winter in freshwater in the Scott and Shasta. They then migrate to the ocean in the spring, generally 1 year after emergence, as silvery smolts about 4 to 5 inches long. Most adults mature at 3 years of age and return to the natal stream to spawn. And lastly, we will be discussing steelhead trout. They also have white gums like the coho salmon, but the spots are on both lobes of the tail fin like the Chinook salmon. Similar to the Chinook, run timing can be distinguished by when the adult fish re-enters fresh water. We will discuss the 2 run timings that we currently have the most information for in the Klamath, winter and summer steelhead. Less information exists for other run timings for various reasons, such as high flows and funding constraints. Klamath Basin adult winter steelhead enter freshwater between November and April. They spawn soon after arriving on spawning grounds and then migrate back to the ocean in March or April. 1/2 to 2/3 of the Klamath winter steelhead spawn more than once during their lives. Fries emerge from reds beginning in April, and juveniles can adopt 1 of 3 life histories, though the first is the most common in the Klamath. The first life history is to spend up to 2 years in freshwater before migrating to sea. The second life history is a freshwater residence strategy. This accounts for about 10% of the population. The third life history is to spend 2 or 3 years in freshwater before migrating to the sea. And some juvenile steelhead spend 2 to 4 months in the Klamath Estuary or Pacific Ocean before returning to freshwater between August and October. These immature fish are called half-pounders and are likely to survive and spawn multiple times during their life. Summer steelhead spend summer months resting in pools with consistent cool water temperatures as they mature, waiting for winter rains to spawn from December to February. Summer steelhead can tolerate slightly warmer water temperatures than salmon, but seek refuge in deep pools with cool seeps and springs. After spawning, adult fish migrate back to the Pacific Ocean around March. Juveniles leave their natal tributaries from April to June to feed and grow in the main stem and estuary habitats before entering the ocean. Next, we will discuss fish habitat needs. Habitat needs of salmon and steelhead are very similar, and I have provided a list here of some primary needs. They both need cold, well-oxygenated water. It is important to note that cold water holds more oxygen than warm water. They also need healthy streamside vegetation. This provides shade, which is necessary to keep water temperatures optimum for fish. Large woody debris in stream provides fish with cover from predators and shade to help keep the water temperatures cool as well. Salmon and steelhead also need an assortment of stream bed materials available for building redds, providing scour to river bottom algae, and depositing fine materials for seed deposition of riparian plants. A meandering stream channel with well-defined pools and riffle sections is most preferred. This provides areas of higher and lower velocities for times when fish are feeding versus resting. The meandering channel also slows down the rate at which water leaves the watershed. This will provide higher in-stream flows for longer. Undercut banks on the outside river bend with sufficient vegetation to prevent erosion and bank failure are great locations for resting fish. It also provides cover from overhead predators. Activities that can degrade fish habitat. Increased sedimentation from forestry management, agricultural activities, wildfire, and roads have the potential to impact fish habitat. among others. Too much sediment can lead to the river channel lacking habitat complexity that is needed for good fish productivity. Pools will fill and the channel will elevate. This leads to increased water temperatures and fish migration barriers. Streamside canopy removal is one activity that contributes to both increases in sediment and water temperature. Clearing the stream of woody debris is also detrimental, as this depletes fish habitat complexity and eliminates places fish can hide from predators. Next, I will present the current Scott and Shasta distribution maps for Chinook and coho salmon, as well as steelhead trout. This is the current distribution of fall-run Chinook salmon in the two watersheds. I will use these same maps for the following two species, so I would like to point out the confluence with the Klamath River for the Scott on the left and the Shasta on the right is at the topmost end of the blue lines. The blue line is the river and its tributaries. Chinook in both watersheds, as you can see, utilize the main stem as well as tributaries when accessible. Next, we have these same maps showing the coho salmon distribution for each watershed. This is very similar to the Chinook distribution map. Coho adults and juveniles use both the main stem as well as tributaries on the Scott and Shasta for both spawning and rearing. While there are site-specific preferences in each watershed, distribution tends to be varied based on river connectivity during migration as well as during rearing. And lastly, these are the distribution maps for steelhead trout. Please keep in mind when viewing these maps that we have less information for steelhead due to flow conditions during spawning that has limited our ability to survey safely. As seen with coho and Chinook salmon, steelhead are utilizing main stem as well as tributaries in both watersheds. Next, I will be talking through a few of the practices you can do on your property that will help protect the resources you currently have. These are known as best management practices. Today, I will discuss 3: fish screening your water diversion, establishing and respecting filter areas, as well as minimizing and stabilizing exposed soils. Fish screens are essential to protect adult and juvenile fish from entering irrigation ditches. CDFW can assist landowners with obtaining a fish screen for their diversion. These bullets are some of the operational guidance that we provide to landowners. Maintain connectivity between the head gate and the bypass outlet and fish passage at the diversion structure. Operate head gates at the end of the season to ensure fish have opportunity to return to the creek. On-site consultation is available with CDFW and/or the watermaster. Manage tailwater to minimize warm water flowing back directly into the stream. Use alternative stock water during base flow until the fall rain improves river conditions. And as always, leave as much water in stream as feasible. Establish and respect filter areas. Establishing and respecting filter areas in the watershed are critical to a healthy aquatic environment. Filter areas refer to the vegetative areas that border water bodies, including the riparian zone and forested habitats. These areas perform critical functions in maintaining water quality, including the filtration of debris and sediment from runoff, and the filtration of nutrients, pesticides, or other pollutants that may be present in runoff water or are bound to sediment. The streamside vegetative roots are important for reinforcing soils and preventing erosion, and fencing away from the high water mark will ensure protection from grazing animals. Leaving snags and other debris in stream will slow the flow, collect sediment, and help form these complex habitats. The image on the bottom is typical when filter areas are removed from a river system. The channel becomes narrow and steep, water quality is poor, and water leaves the system much more quickly. One critical function of wetlands is their ability to store water, which is later released into the surrounding ground and watercourses. Changes to the landscape, such as construction of agricultural fields, roads, and crossings, can affect the movement of water within or through wetlands. This may in turn impact the amount of water that a wetland can store, the degree of flooding that occurs, and the rate at which water is discharged from the wetland. Minimize and stabilize exposed soils. The stabilization of exposed soils is essential for reducing and preventing erosion. In some situations, planting or seeding of vegetation might be required to stabilize soils to prevent further erosion. Temporary materials that can be used for stabilization include hay or straw, brush, slash, or erosion control blankets. More permanent options include wood chips, wood waste, bark mulch, and permanent erosion control blankets. Enhancing fish habitat. In addition to best management practices, there are actions a landowner can take to really maximize fish productivity within the river. I will briefly review 4 of the most common restoration practices occurring within the Scott and Shasta rivers today: off-channel ponds, beaver dam analogs, in-stream wood structures, riparian plantings, and riparian fencing. This diagram is an example of engineered plans for a restoration project implementing many of the features I will discuss. Off-channel ponds. Off-channel ponds are constructed pools adjacent and connected to the mainstream river or creek. The ponds do not divert water from the creek. They are dug into the water table and have one surface flow connection to the creek to allow for fish to move in and out of the pond. The surrounding area is seeded with grass and willows are planted. High numbers of coho salmon have been documented using these habitats around the Klamath Basin, as they provide the preferred slow, low-gradient habitat. The connection to the water table provides fish with cooler temperatures in the summer and warmer temperatures in the winter, both needed for growth and survival. Beaver dam analogs. A beaver dam analog is a man-made structure designed to mimic the form and function of a natural beaver dam. These structures slow down the water that's leaving the watersheds. This allows more time for recharge to the groundwater table, which in turn provides more cool, clean filtered water to both the Scott and Shasta rivers. As mentioned earlier, cold water is essential for fish production. Slowing down the water behind the dams also provides fish with a resting location that is absent of velocity. In-stream wood structures. Wood structures are designed, then built and anchored in stream. They create a resting place for fish that is out of swift river velocities and contain in-stream cover to protect fish from predators. Geomorphic stream functions return, such as gravel sorting, sediment retention, and floodplain connectivity. Upstream riparian seeds and plants are received and retained within the fine sediments of these structures, which helps to restore those riparian habitats within the river corridor. Riparian planting and fencing. Planting riparian trees is an important action you can take on your property to improve the health of the river and the aquatic organisms it supports. The plants will stabilize the stream bank, which minimizes erosion, a benefit to both the landowner and the fish. Water quality will improve as well. As stated previously, riparian plants filter nutrients and provide in-stream shade, which lowers water temperature. Fencing the riparian will also be necessary to ensure the plantings can get established. Once established, there may be a need to develop a longer-term management strategy of the area with local professionals. Funding opportunities. The California Department of Fish and Wildlife has numerous funding programs available to assist landowners in the protection, restoration, and conservation of fish and wildlife resources. We currently have funding programs divided into the following categories: drought response, fish and wildlife management, and watershed restoration planning and protection. The online grant portal can be found at the web link you see here. Each funding program is identified with a hyperlink, allowing you to access all the information needed on the funding priorities and objectives, the necessary application materials, relevant workshops, and a program contact for more assistance. And this concludes the presentation today. Thank you for joining. If you have any questions from the presentation, please email the address that you see here. Thank you.